Good evening and welcome everybody to Ensign Flight Switchenko. This is Obi-Wan Pez. Sorry for that awkwardness there. Just checking something. Making sure that the whiteboard was working properly and all that. So, how's your week? Mine's been a little weird. Had a few random meetings. Hey, Brad. So yeah, hope things have been going pretty well. Had some other stuff going on this week. Mostly just dealing with end of semester stuff. Decided that I was going to basically rewrite all of my course's objectives. So we'll see how wise of a decision that is, or how long it's going to take me. So, Brad, welcome in. If you have any questions, let me know, and I will be happy to answer. I do not have a public Discord server now. I may at some point, but not any particular, possibly not in the foreseeable immediately foreseeable future. Alright. It's probably enough messing around. For tonight, may break out the mathematical thinking book again, and start looking at a couple of other pieces that are in here. Good evening, Archibird. How are you? Well, at the moment, I'm just wasting time sitting here instead of actually doing something interesting, so apologies. But if there's any particular questions you have about math, any particular subjects, topics that your teacher had gone over and just like not quite clicking, I can attempt to give you something, hopefully something interesting to think about. Alright, so maybe to kick something off, let's try... There we go. Yep, absolutely. And again, like I said, any particular questions, let me know. Alright, so let's see. I've got a problem here. So the American Mathematical Association of Two-Year Colleges, or AMATYC, puts out a periodical that has all sorts of problems at the back. And, oh, differential equations is one of my specialties. Hopefully we can have you be glad that you came here. That's the ordinary differential equations, right? Because I've also taken partial and nonlinear, but that stuff, it's been a long time. I've tried reteaching myself partial and I can't get there. There's like a couple little humps that I need to get over before I can actually do it. Alright. So, an interesting problem here. Now, granted, I have only just started looking at this, so I can't guarantee any particular answer, but we'll see how it goes. Really? You're not going to autocorrect that one, you'll autocorrect all the rest of them. Okay. Close enough. Alright, anyway. So we have a... what happened? There we go. We have a cylindrical glass of radius r. And height h. That is filled with some incompressible liquid up to height lowercase h. Where h has to be little h. Needs to be between half of big H, so it's more, the glass is more than half full, or at least half full, and is not to the top. So an interesting problem here. At what angle alpha is the liquid going to begin to spill out? So, I did also say I don't necessarily know what this is going to be. I don't necessarily know how this is going to work. But so let's suppose that we're going to tilt this way. This point H is going to be listed as here. If the glass is at least half full, I think this means that the water is not going to get to the bottom of the glass before it starts spilling out the front. Just hypothesis here. This is pretty close to halfway, but just slightly underneath. So this is going to get to the bottom of the cup before this starts spilling out of here. I like to live life dangerously. Right over the top of my keyboard. All right. So let's see. That's going to start creating a shape rotate that way. That's going to create a shape which looks vaguely like this. Alright, and three-dimensional. So how do we find the volume of this particular shape? It's basically a cylinder that's being chopped by some plane. And then we have to do some calculus to manipulate it as it's tilting at angle alpha. Wait. No, from vertical. Or is set equal to, yeah. So if we do this like this, right, we've got I think we can start. Now I don't know exactly how to really go about this, but let's start with maybe a coordinate system. So we got 0, 0. This is going to be, is it? Nope. R. R0. And this point here is going to be our little h. And we have here big R, big H. This might be completely absurd, but you know. Alright, so alpha is in the negative direction. So then this point here, let's say our final position, where we want this to be. This is still H, this is still R. Alright, so if this is transformed by alpha in a circle, then this location here is going to be, right, R, big R, cosine negative alpha, which ends up just being the same as R cosine alpha. Could be. So I think the problem is that, oh, that hypotenuse. Yeah, okay. I think it might. So I'm thinking that what's going to happen here is we need to do calculus on where on the shape, no, on the major height of this truncated cylinder. Find out what that height of the truncated cylinder is going to be based on what angle we're tipping everything at. So well, you're saying if we do this, right? Might be able to figure out something here. This is just the same as complement of alpha 8. So this is going to be, I know. Pi over 2. Yeah, it's going to be really more convenient to do this in terms of pi. Maybe. Alright, which means that this is alpha. Alright, maybe we'll just do that. Alright, let's see. Also, we can do one of these. If we create a right angle, or a right triangle going that way, right, these are going to be similar. So the angle that it has been dropped by is going to be alpha here. Similar triangles might be sort of nice. We won't be able to necessarily figure out the angle perfectly, but at least we get some relationships going on. Alright, so this is like our deviation in the x direction and our deviation in the y direction for our point here from the location it came from up top. Let's see. So delta x over r is going to be equal to the cosine of just alpha, right? Because that doesn't actually matter which one it is. I was right on that one. Okay, so delta x is equal to r cosine alpha. Alright, so that's that. And then similarly for delta y, it's going to be r sine alpha. Keep doing that. Okay. So from here, got a couple of other options. Maybe. So, let's see. Is it really just going to be a factor of how far it was up? We'll let that one through. That's fine. Well, not every time. Come on now, Twitch. Right, so if we look at this originally, right, so Let's just start naming them after Python variables. That's fine. Get rid of that. Okay, so the volume here is equal to pi r squared. That's a terrible idea. R squared times our height here. So this volume here also has to be pi r squared height, but it's been tilted so the shape is different. Alright, this has to do something, this has to like have something to do with a, how does a frustum work? It's not a frustum though, because it's not a cone. So this has to, okay, we can do like a cylinder for the other part of it. Up to here. Let's turn that down to a 2. That's going to be its own. No. It's going to be its own height. That'll be a lowercase. HT for tipped. Alright, so pi r squared HT plus. This is not going to be a nightmare, it's fine. That other part, what is that? We could probably integrate that. My Calc 2 students would be pretty upset with me for trying this. So this has it's a cylinder, but it's being bisected by a line. You know nothing of madness. Okay. Wait. Hang on, hang on. I think I got maybe. So if we were to turn this into its own revolved solid, and then say that we only want to count the part. This may not work. It's wishful thinking, really. But that's only if the whole thing is really getting smaller. It's not quite. All right. No. Okay. Yeah. Should have known. Yeah, it was what I thought it was going to be in the first place. So it's because we're basically treating this, or we can basically treat this as like a three-dimensional representation of, or like a revolved version of a trapezoid. Because of course. Alright, so let's back it up a bit. So, I do actually need that, don't I? Alright, so h sub t. Gonna be pi r squared times, it's the average of the two heights. So h sub t plus big H all over 2. Since both sides also have pi and r squared, that can just go away. So we just got h is equal to h sub t plus big H over 2. It's going to be 2h equals h sub t plus big H. So we want the tipped height. Yeah, okay. So tipped height is going to be equal to 2h minus big H. And we know that this is okay because, again, 2h had to be... I don't even know if you can actually see that. Okay, there we go. So 2h had to be bigger than big H in the first place. We said at the top that was one of our conditions, was that we had to have here big H over 2 is less than or equal to small h. So we have to be at least at the halfway mark. So little h sub t, I was right. If it is exactly filled to half, we'll hit the bottom here at the exact moment that water hits the top rim here. Alright, so my intuition pans out there. That's good. So then at what angle is this going to occur? So h sub t has to be equal to 2h minus big H. And then can we create a right triangle here? Yes, could potentially create a right triangle here. I like it. Okay. It's gonna get in the way, unfortunately, but we'll make this work. So green, because why not? So here, this is gonna be our right angle. Our alpha that we've tipped. Is the hell is that? Sounds like seagulls or something. That's weird. Yeah, because you don't want a truncated ellipse, otherwise that's going to be a pain. Okay. So where is that? Is this alpha here? Yes. Should also be alpha there. Right, okay. Yeah, opposite interior if you kind of take them like this and then shift them around a little bit. So these are our parallel lines here and here. And our transversal's the diagonal here. So it's going to cut our alpha and our alpha here as the two things. Ah, yeah, these are also. Or the diagonals here and here are parallel and our transversals here. So I'll get. Yeah, there we go. This alpha could be attached here. It's the same angle there. That's also alpha. Right. So we're good here. This is all checking out. All right. So, God, this part right here is gonna be fun. Okay, let's relate this to the other one, delta x. So this means that the cosine of alpha is delta x over r, which is going to be the same okay. So this cosine of alpha is going to be equal to delta x over r, which was the same over here as... Hey, Amogus. Hope you're having a good week. Which in this triangle, the cosine is going to be equal to whatever this is over h sub t. What's this thing going to be? I hate it. Yeah. That's what happens when you accept fascism as part of your life. So. There's a lot of people who wish they could draw. Alright, let's see. That's supposed to have a cooldown. Oh, come on now. Really? Stream elements, please. Where the hell did it go? That's weird. Oh wait, no, it's not even stream elements. Ah, nope. That is in my community. Streaming tools. Nope. Your rewards. There we go. Channel points. There we go. Alright, apologies to limit you on that one, but I'm not going to want to run to the bathroom every 5 minutes, so it's a amateur mistake there. Alright, let's... That's also a possibility. So if we were to go out here and say, I want just a rectangle that's up, you know, or like one of those flat things. When do we end up getting up to this point? Yeah, I think that does work just the same way. So again, this to tip up to this particular point here, at which point, right, our alpha equals 0. Ooh. Right, okay, so that's alpha. Interesting also. Yeah, that's going to take a while though. If this is alpha here, then this is going to be 90 minus alpha, or pi over 2 minus alpha. Or we can draw an alpha in here if we really felt like it. Eh. Okay. Yeah, because all we need really is, like, area. We don't even need to worry about the volume. Well, okay, the area and the volume is going to do the exact same thing as we did earlier. Right, so area here is going to be equal to our base 1 plus base 2 over 2. Again, this is h, which takes the place of base 2. And then here, whatever. This was our h sub t from before. Alright, multiplied by, this would be 2r. Right, as the height of this whole thing. So, yeah, this is just area equals t plus h. Now I think this is going to do the same exact thing as what we had before, times r. It's going to be equal to, in this case, this was little h and 2r. On this way, yeah. So h sub t is going to be equal to, our r's can divide out, and then we get 2h minus big H, which is the same thing. Like, we knew that that was probably going to happen, or we knew that should happen anyway. Right, so same. All right, and then what was the thing we needed now? So, like, big H, little h, not h sub t, but little h, and all this other stuff are all found. Like, we know what it's going to be. So we're basically taking this thing and just tilting it until the water starts to pour out. But it has to be more than halfway filled in order to ensure that the bottom doesn't then become truncated. So we want it to still be an ellipse. Right, so that's really the important thing here, was just that. And then, yeah, what is this all gonna measure out to be? that's also alpha. This height here and that height there is, man. That does not have anything to do with anything else necessarily. Okay. Just checking. Oh. Oh. Pff. Duh. How about that big giant triangle right at the top? Right there. That one. Okay, so yeah, if we assume that that's a rectangle, it's going to be that right angle there. This alpha is the same as that alpha. That's a complement. That's also a right angle, so this is alpha. Which means that this is pi over 2 minus alpha. Yep. Alright, so then this part here is going to be 2r. This part here okay, right, equal areas. They have to have equal areas. So this area here has to be equal to this area here in order to make all this work in the first place. So yeah, okay, I gotcha. H2 is equal to it's 2r by capital H minus r and minus little h. Nope. Which has to also be equal to this one here. 2r by... That's interesting. That can't be right. Okay, what'd I do? Oh, no. That's not a rectangle. 1/2. Okay. So if these things are equal, then their radii can be divided out without question here. So this is going to be 2h, capital H minus 2 lowercase h equal to uppercase H minus h sub t. We just got the same formula. All right. That's literally that. Oops. But. Right, but. Right, okay. No, I got what you have now. So, that doesn't matter. That's a good way to verify it, but it's not what we want. We can then say, all right, give me the tangent of this thing in order to figure out what this length is here. So that whole length is twice capital H minus h. Yep. Because that's big H minus h sub t gives us this thing. Okay. So yeah, this is now going to be that's all right. All right, so the tangent of alpha has to be equal to twice big H minus h divided by the other side, which is 2r. I gotcha. All right. Which is equal to big H minus little h all over R. Okay. Woo! Ah. We got there in the end. I like it. Woohoo! Yeah, just some random problem that's out of the out of this MathAMATYC or MathAMATYC Educator. I see. Okay, so oh, interesting. All right, so this is A or G1. G2. Solutions to problems in this issue are due by 25th January 2023. That means that we could actually write this up. Oh man. Okay, what is the greatest value of B such that b to the x equals x? Ugh. It's like writing shorthand. Has at least one solution. There should just be a rotation button, but I'm not sure how to make it look like you've got, what the hell? Ah, great. I apparently have a bug inside my monitor. That's awesome. I don't know how that even happens. It's a literal bug. Alright, give me 1 minute. I'm gonna say goodnight here, and then... Anyway. I'll be back in like 2 minutes. Alright, so... Because oh, you know what? Is that my problem? Am I listening to this? No. Okay. Thought I had myself playing here, so that'd be kind of awkward to... be like echoing. Okay. So... we want to know of a particular e to the... nope, not e. b to the x. Find what is the maximum possible b such that these two things have an intersection point. Alright, so this is not going to be a clear... this is not going to have a nice, clear answer due to the fact that... When you set these equal to each other, it becomes a mess. You can't take the log of one without messing with the other. So maybe there is a different way of looking at this, just like the other problem, right? There might be some different way of looking at this, such that we could come up with a nice solution here. So Okay, so in order for them to intersect, they're going to have, and only once. So let's go for the minimum solution here. In order for them to intersect only once, they have to be tangent. And so it would be that the slope of y equals b to the x would have to be the same as the slope of y equals x, which is 1. So we know that much. So if we take the derivative of both sides, and this is going to get us, so b to the x times the natural log of b times dx needs to be equal to just dx. Okay, so this is going to be 1 on both sides. So then b to the x times natural log of b must be equal to 1. So the natural log is going to slip out to the other side. This is b to the x equals 1 over natural log of b. And then here you can take the natural log of both sides. Let's go with the thin one. Okay, so that means that we've got x natural log b is equal to the natural log of 1 over the natural log of b. And if we want to, I guess, we can give this a negative exponent, slip it up. Natural log of parentheses natural log of b raised to the negative first power. So that can slide out front, make this negative natural log of b is equal to x natural log b. So then x... Really? So yes, but it's really quick. So Archer reminded me that, couldn't we just make this into a rectangle and skip the whole, like, cylinder thing? And I was like, yeah, actually, that's a perfect solution to be able to figure this out, because then you don't have to worry about volume. You just worry about the areas of things. So, one, it turns out that from the two areas that we get, the area of this... nope. The area of this stuff up here, the air in the glass, and then here, the air in the glass when you tilt it, those have to be the same areas. So you get 2r, keep tapping this thing, 2r times big H minus h to get you the area of this one. And then same thing over here, but it's 1/2 times 2r times big H minus little h sub t. So that's now a triangle. And when you relate those, you do end up getting h sub t equals 2h minus big H, but, and the important thing is, big H minus h sub t is this side of a right triangle. And then here you can say, oh look, I have an angle here, and I have the opposite and the adjacent sides, so I can use a tangent. Right, and that's what all that is up there. So alpha is going to be equal to tangent inverse of big H minus h over r. Yeah, no worries. All right, and then we moved on to G2 here, which is the second unsolved problem. So what's the greatest value of b such that b to the x equals x has at least one solution? Well, in order for that to have only one solution, they have to be tangent. And so if they're tangent to each other, they have to have the same slope. So therefore, the derivatives of both sides have to then be the same thing. And that gets us to, again, eventually work down to this massive, nasty stuff down here. All right, so x is going to be equal to negative natural log of b, all divided by the natural log of b. And I don't think we want to use that as another exponent. Natural log of the natural log of b raised to the negative natural log of, or 1 over the negative natural log of. So yeah, I think we're going to call that there and say that, all right, look, x is going to be this thing. And then we have to have a largest value of b to make this work. So I think maybe we just solved it the wrong way. I'm going to hypothesize that it's E, but it's probably too big. So let's see what happens here. So if x is equal to that stuff, so if instead we went with like e to the b to the x is equal to e to the 1 over natural log of b, does this do anything? Possibly not. Or e to the natural log of b to the x is equal to 1 over natural log of b. Can try it this way too. There's a bunch of stuff we can do. It's not necessarily going to lead us anywhere, but Yeah, okay, this is all the same stuff as what's over here. Um, oop. Max Will, thank you very much for the follow. Um, if you have any questions, my name is Obi-Wan Pez. This is N-Simplex Pachinko, and hopefully if you have any mathy type questions, you can feel free to place that in the chat, and we'll get to you. Right now we're just kicking around some problems that are kind of fun, so not super important. You can feel free to interrupt. So right now we're working on some stuff that is out of MathAMATYC Educator. That's a publication put out by the American Mathematical Association of Two-Year Colleges, or AMATYC, of which I am a member because I get this periodical every so often. Periodically, you might say. Nice. I don't do reviewing, but I mean, you could send it to me, but that doesn't mean anything. By member of AMATYC, I don't mean like the review board or anything like that. I just mean I pay dues to them, and they send me a magazine. Can give it a shot if you want. So the channel name at gmail.com is my channel email, and I should be able to, at the very least, take a look at it and see what you got going on. That doesn't make any sense. Hector, thank you very much for the bits. How are you doing this evening? Okay, so can't just be. Yeah, sure thing. I'll take a look at where is next question. Which window is this in? Because if it's in the window that, yeah, you know what? It's in the window that I'm looking at right now, so we can't look at it. Just or can't. Anyway, I'll take a look later. Okay, so there's a problem here in that our x value has to be equal to this thing. Now, I just plugged in e to see what would happen, and e comes back with natural log of e at the bottom is 1, natural log of e in the middle is 1, and then the natural log of 1 becomes 0. So this means that x is equal to 0 gets us a slope of 1 for the function e to the x, or y equals e to the x. The problem with that is that it very clearly does not reach that slope. Or it very clearly, if it does reach a slope of 1 at x equals 0, then it's not going to continue out and connect with y equals x. It's just not going to happen. So, we need numbers that are smaller. So, e is too big for this to work, which means that not only does x need to be this for the derivative, but x needs to be this for the original equation too. B to the x equals x. Right, because that's where they need to intersect, and also that's where their slopes need to be the same. Can't make s's in here. Okay. Gradients. Little player in. Yes. So gradients of a line is going to be a little weird. Gradients of a surface is better explanation for it. You're talking about some sort of XYZ equation. So if x has to be replaced by all this stuff, b to the negative, nope, negative natural log of b over natural log of b okay, equals negative natural log of b over natural log of b. Gonna come back to that. All right, so gradient. Basically what you're looking at is the gradient at any given point is going to be the vector of steepest descent. So if it's literally the gradient of a line, it's going to be the slope. Now if you have a surface, long periods of staring oftentimes is what you need. I am unfortunately out of coffee, so that's... Alright, so vector of steepest descent. When you're looking at this, you're looking at the del of a particular surface, which normally we let that be just like S or F. Yeah. At some point, x0, y0, z0 is going to be equal to partial derivative of f with respect to x, comma, partial derivative of f with respect to y, comma, partial derivative of, nope, of f with respect to z as a vector, and then that's going to be evaluated at x0, y0, z0. Alright, so you got some point down here. You want to find the gradient of this particular area. It's going to be, let's just say, down this way. Alright, so let's go with like, I don't know, 3 x to the third plus 7y squared minus z equals 10. So if we wanted gradient f, this is going to be taking the derivative of these three things and saying here this is going to be 9x squared, comma, partial derivative with respect to y is going to be 14y, partial derivative with respect to z is going to be -1. And at 3, because I'm just obsessed with 3 apparently, 1, -2. It's going to be 3, comma, -1, comma, -2. Nope, 1, not -1. Which is then going to be 9 times 3 squared by 14 times 1 by -1. Which is going to be 81, 14, -1. Okay. Well, that's going to be fun. Is the natural log of b. Oh no, that would be a... Sure. Let me ditch this a sec. All right. Okay. I see what this is. Yeah, I get it now. Okay, so yeah, I'm basically explaining some stuff that is in Calculus 3, which is not helpful. This is extremely. You can't see this. Yeah, this is extremely, very much more complicated than we need to do. Okay, so gradient. So in like algebra terms, gradient oftentimes, at least in the United States, is also known by the name slope. And that's to distinguish it from the gradient being the three-dimensional gradient, which is the what I said above, the steepest descent. Yeah, vector of steepest descent. So when you're talking algebra, then you're talking slope. So yeah, no, this has nothing to do with it being an old book. This is just me not understanding which sense of the word you meant. Yeah. So slope is going to be a measure of steepness. Of a line. So way easier. Um, so when we're looking at this, we want to know, oftentimes we'll call it M, again, in the United States. This is the change in our y values divided by the change in our x values. The change in output over the change in the input. And if we're feeling particularly technical, we could talk about the dependent and independent variables in regards to that. All right, Archer, have a good night. See you later. Probably see you on the video on demand, or you will see me on the video on demand, and or we can try again next week on Wednesday. Just for random stuff, because I haven't said it yet. I do stream on Wednesdays, is always math night, and Fridays are always kind of a game night. So I've been doing Valheim recently, have done Elite Dangerous, and a number of other various games just for fun, because why not? So, hope to see you all later, or hope to see you later, Archer, and anybody else who's stepping out. Anyway, so for our slope, or for our gradient, algebraic gradient, you're going to look at the change in the dependent variable versus the change in the independent variable. So let me mute this again, and that's not the one I wanted to mute. No, that one. Let me pull your examples up, like, actually. Okay. All right. So you got something that basically looks like this. I'm not even going to put numbers on it. You can see it from where you are, and you know, I don't want other people to just answer for you. So that's how we roll here. All right. So Takahiro measures the height of bamboo shoot at the start of each day. Bamboo grows very quickly. The graph shows the height h in centimeters. Oops. Height h in centimeters after a certain number of days t. Okay, use the graph to find So let's do the easy question first. This is question D1. What is the height of the bamboo going to be after 5 days? All right, 50 centimeters works out very nicely because, again, what you do is you come down here, you just say, okay, this is going to be 1, 2, 3, 4, 5. This is day number 5, and we trace this up to this particular level, which then trace it over to the side. Right, that's going to be 50. Alright, so height of the bamboo in centimeters. And time in days, right? 5 matches with 50. Alright, the other one, D2 then, after how many days will the bamboo shoot be 35 centimeters? $350 days. No, it was 35 centimeters was the question. Yeah, that's all right. Yeah. So 2 days matches with, we got 35 here. Trace over, match where it is, and then trace down. Now, this is not an accurate graph by any stretch of the imagination. I'm just making this up to sort of look like the one that's actually in your book. So, you know, just keep in mind it's not to scale. All right, so then let's go back then to part A and say, what's going to be the y-intercept of this particular graph, equation, line? What's going to be the y-intercept, and what does it mean? Yep. So y is equal to 25. You always match that up with our x equals 0, or t in this case is equal to 0. So here, that's our y-intercept location. I don't know how your teacher feels about it. I will always insist that the y-intercept, if it's referred to as the y-intercept, needs to be a point. So 0, 25. If your teacher says it's going to be, in this case, not y, but h, right? So h equals 25 centimeters, then you can go with that. That's fine. Right, so technically it's not even the y-intercept. Technically, this is the h-intercept. It's not like it's wrong, it's just, you know, you gotta remind yourself which variable is my independent variable, which variable is my dependent variable, because that does matter later. You can actually have a y value, or a y variable as your independent variable. It all depends. Right. So anyway, 0, 25 is going to get us our y-intercept. And then what does it mean? And anybody who's not sure what it means, like, this is why I write it out as a point every single time. Because here, this is describing two pieces of information, and in your explanation, you need to describe those two pieces of information, not just one. Well, not really. So, I see. Interesting. Okay. That's something we could work with. Whoa. I hit a thing. Hang on. Okay, so looking at it like that, really you're looking at the slope of this thing is, you can't think of it as just like two numbers like that, where you have, okay, it's 25 and x. It's a difference between two different locations. And it's important that it's two different locations. We'll see why in a minute, but so I'm being a bit of a jerk here. So your y-intercept is going to be 0, 25. What does that actually mean in terms of the problem? What does 0 mean? What does 25 mean? Okay. So, which variables do these two things represent? So you already said y, or in this case h, really, is 25. So what variable represents our 0? Or which variable is represented by our 0? X, or in this case, because again, I'm just being me here. Yeah, T. So, with you having a T value and an H value, what does it mean in terms of, like, what it's describing? What this graph is describing? Yeah, like this particular point, 0, 25, which represent the variables t and h respectively. What do those numbers mean, there we go. What do these numbers mean for these variables? Mm-hmm. And specifically, describe them together. Okay. So read them in order, right? T represents what? Yeah, but what does it represent? What are the units that we want to use? What are the, like, what is it describing? Yeah, so when t is equal to 0, now this is not a good explanation. This is just literally what's being written. Yes. I hate this whiteboard app, but it doesn't crash my computer, so... Okay, so at 0 days, when t equals 0, what else is happening? Mm-hmm. Yep. Yeah. So this is where we want to be. You can say whenever you see any ordered pair, it doesn't matter what ordered pair it is. The first thing you want to do is label like which variables do these represent. So your independent variable, t, is the thing that just keeps going on no matter what. Or maybe it's the thing that you use as units in order to measure something else. You know, the thing that like our experiment is just going to naturally change. Usually it's time if you're doing something with a scientific experiment. Sometimes it can be like, what are we varying? So, for instance, like if I invite more people to a party, it's going to cost me more. So the cost of a party compared to the amount of people I invite, right? The amount of people I invite causes the cost of the party to go up. So the independent variable is going to be the number of people I invite. It's the thing that I can change. It's the thing that I can, like, directly affect. And then we want to see what the effect is. So we'd say, okay, the cost of the party seems to be going up as we invite more people. That's very strange, isn't it? Not at all. In this case, again, as long as we wait longer, the bamboo is just going to keep getting taller. Because, you know, that's what bamboo does. And the same can be done with a height chart for a human or anything like that. Over time, the human grows at a, at a different rate, but it increases kind of steeply and then starts decreasing once they reach about where they're going to stop growing. Anyway, so the first thing I'd want to do is label which variables are which in your ordered pair. The second thing I would do is, at least in your head, you don't have to write it, but do something like this. When t is equal to 0, h is equal to 25. Just think about it in terms of raw math. What are the numbers representing in terms of the variables? Then you think of it in terms of the actual problem. So then you say here, at or after 0 days, after no time has passed, the initial reading is 25 centimeters. So this is the initial measurement of this bamboo, 25 centimeters. And this is really one of the better explanations that you can make, because it explains what you're measuring, how you're measuring it, and what units you're using all in one. Specialty dish. Good evening and welcome. I am Obi-Wan Pez. This is N-Simplex Pachinko. We are doing some algebra and talking about the slope or gradient. 3 calculus books. Killer King, hey, how's it going? Yep, specialty dish. Evening. If you have any questions, let me know and we can try and work. Oh, yeah, no problem. No worries at all. I do that all the time, so you're in good company. Okay, so that is the y-intercept. Is again either, depending on what your teacher wants. The y-intercept is either going to be just like h equals 25, or as a point 0, 25, and how it represents, or how you represent it, is then, or how it represents the situation is after 0 days, the bamboo height is 25 centimeters. Go with that. Okay, then we go to part B, which is now find the gradient of the line. So again, gradient is going to be the same as slope, which we said has a calculation in order to find it of m is going to be equal to delta y over delta x, or the change in. So the change in on these sort of things is going to be, how does it change from one thing to the next? So in this case, you have to have 2 different points. We've got 3. So you can choose which pair you want to use. It doesn't really matter which ones you're going to use. I tend to stick with low numbers, stuff like that. Specialty Dish, congratulations on graduating recently. So, as in like last week. And again, if so, congratulations. Yep, I'm a big fan of the math channels we have. Unfortunately, I've only seen about 3 or 4 others, and many of them are currently... What the hell is going on? Come on now. Many of them are currently not running anything in particular. So, I know 2 others especially. I'm going to spell it wrong again. Yeah, Tayo Inoue is a good streamer. He's not on quite as often as he used to be. And shout out for Megalomorph. So these two individual people specifically do like science and technology streams, but it's math. They just don't go under the math section. Megalomorph is grad student, maybe a lecturer. I forget. Sorry, Megalomorph, if you're here, I'm very sorry. But yeah, I really like the two of them. I don't see Tayo on too much anymore, but I think our times also are really off. And I've got a few others, but like I don't remember what their times are. But anyway, yeah, like I said, I really like them. Back in December. Okay, nice. Yeah, Martin Gardner has such an amazing, like, way with words about him. Thompson, interesting. I don't think I've heard of that one. I'll have to look that up later. And, okay. So, little player in. Not quite. So we still don't actually have a change in your y's and your x's if you're just saying, okay, I've got 0 and 25. Right? That's not the change in those things. That's just a value. Yeah, that was one of the things that I did was I actually looked for specialty dish. I looked for math in the title of the video, and I looked for video on demand. And so when I did that, I fell across a bunch of these channels, and I was like, oh, well, that's interesting. And I started streaming. I started streaming not too long after that, and said, all right, you know what? Let's do it, and let's throw it in math, because why not? Besides, it makes people twitch when I go into channels and they're like, let's do a shout out for Ensiplex Pachinko, and then they're like, math. Always makes me laugh. All right, so little player, right? For our slope, what we want is the change in these values, or the change in our y variable, which is h in this case, divided by the change in our t variable. So, like I said before, we need 2 points in order to do this. So, in order to determine change, one of the things that we can do is say, okay, let's say we have a point here, and we have a point here. Now, if we go with something like 1, 3, I'm just going to make up a couple of numbers and make it sort of easy. 4, 8, for example. Let's see, is that going to be adequate? Sure, why not? Then what we want to do here is, again, look for how do we find the change in these values. So if we just look in the x direction, we say here, just in the x direction, it's going to be this distance between this particular point here and this particular point here in just the x direction, just the horizontal direction. And so how would you figure out what that distance is to go from 1, 3 to 4, 8 in just the x direction? Nobody else answer. you know, no offense. We can have all our side conversations too. So. Right. Yep. So we look for the difference between these two things. Yep. And with whole numbers like this, it's real easy to just do, right? So you start at 1, you go 2, 3, 4. Oh, look at that. It's a distance of 3. But that's perfect. You already know how to do that, and that's great. So 4 minus 1 gets you 3 for that total distance. And then again, to go from the bottom here at 1, 3 to 4, 8, we're going to show it as Calculus Lifesaver by Adrian Banner. Very nice. I have been reading this last week or so Bell Hooks, Teaching to Transgress. Oh man. Alright, so 8 minus 3 gets us 5. Yep. MAS-1, nice. 35 pounds. That sounds like what I've got under my monitor. So I have this ridiculously large, nice monitor over here, and then I have my old monitor is like a 19-inch, which is really kind of small, and I put that as my like Twitch monitor so that I would be able to put my OBS stuff over here and then be able to manipulate whatever I wanted just to see like what I'm doing, versus over here I get the actual display of, you know, the whiteboard and any other documents I have open. Okay, so here, well, the 19-inch monitor is so much smaller that I have to prop it up in order to make sure that when I drag my mouse from one screen to the other, it doesn't like jump a foot. So I figured it out. I made it so that it like is approximately correct as far as where I am, like where I'm normally sitting here or here. It's like within an inch anywhere on the entire screen, so it works out kind of nicely. Okay, so we get our delta y, or again delta h. Why is it doing that? And then our delta t here. So not quite. Remember that this is delta h over delta t. Megalomorph, yes. Speak of the devil and he shall appear. I don't want to give you that much responsibility, I suppose. So by taking these things, m is going to be equal to our delta h, which was 5. Yeah, over our delta x, delta t, whatever, is going to be 3. So in this case, we end up with a slope of 5 over 3. I'm sure they did. Oy. Not quite. With some generous rounding, that would be 1.3 or 1.5, but no, that's right, 1.6 repeated. Generally speaking, we're not going to want like repeated decimals. I don't know how your teacher particularly likes it, but generally speaking, improper fraction, in this case 5/3, would be as much as we care to make it. Mostly because if you look at it, this is going to be, it's going to go up 5 every time it goes 3 to the right. So 3 right, up 5, 3 right, up 5. every single time. Or we can make an enlarged version of that. So as you can see over here, right? Okay, this is not the same slope, so I shouldn't do that. Um, but here we start at 0, 25, and we go up to 2, 35, or we go up to 5, 50. And so we can do that with this example. Yeah, I'm in a math class. You don't round. Until the very, very, very end, at which point you say, well, what's reasonable? Honestly, in my class, that's pretty much how it goes. I'm just like, look, just round it to however many it makes sense to round it to. I don't care. I want the exact answer. Which, I mean, is probably a bad idea, but nonetheless. So anyway, if you take 0, 25, and then we said we want to find where that's going to go to get up to 2, 35. So, little player in, where does that go? Yeah, so I was also so not for this example, but yes. No, okay. Crap. All right. Oh boy. Hang on one sec. All right, GCSE maths. Nope, I'm getting the same thing here. Alright, so I'm getting the same thing where the gradient is specifically looking for the change in the y value divided by the change in the x value. So either... I hate saying like your teacher's wrong, but there's the possibility that your teacher got them flipped backwards, or you misremembered, or I don't know. There's some other stuff that could be happening there. I mean, it could be that you all have a different definition for it, but somehow I don't think so, just because that's what I was checking, was to see if, like, you know, different countries just call it something different. It's possible, but the one I saw for GCSE in... Okay. The one that I saw for GCSE in England was specifically saying, yeah, that slope and gradient are the same thing. So this is also true for engineering, and there is, like, for instance, on steep hills, if you've got a hill that goes like this, and I was in the mountains this weekend, so you can't see that. I was in the mountains this weekend, so I had a chance to see something like this. It said that this had a 5% grade. Yeah, anything's possible. All right, so a 5% grade means that this will go down 5 feet for every 100 feet they go out here. And in fact, this is unitless. It doesn't really matter if it's feet or meters or miles or whatever. So the percentage here is telling us that the ratio between the two sides of this triangle, the slope, is going to be 5% or 0.05. So in this particular case, right, it's going up, if you're going uphill, up 5 units for every 100 units you're going across. So 5 divided by 100, change in y divided by change in x. It's going to be 0.05. Okay. So then here we've got the points that are actually on your graph. So 0.25 to go to 235 is how far? And I got to get out of the habit of looking over here all the time because that's where my monitor and that's where chat is. You're here. And it's super important that these are at right angles to each other because otherwise it's all sorts of messed up. Unless, of course, you're using some sort of, like, slant slope, in which case that's just all messed up. I would not do that. All right, because so how far is the value increasing and in which direction is that? All right, the right side shows us that we're increasing in the... Yep. Sorry. Increasing in which direction and which variable is that? I will not be teaching any classes this summer, at least not for contract. I might end up taking a few, like, sub classes or something like that, but... so here, we're not going 4 to 8. But we don't have those numbers here. So again, we're doing this example here, which is the one from your book, the one with the bamboo. So we're going from 0.25 to 2.35. Yep. So this one ends up being a +2 in the x direction and a +10 in the y direction. So m here is going to be not x though. You're increasing in your y direction by 10. Yeah, over your +2 because that's your change in that particular value. I got you. Okay, so m is going to be 10 over 2 or then 5. 5 over 1 if you feel like it. Again, it kind of depends on how you can justify it, or if it's meant to be typed into a computer to give you an answer, or for you to give the computer an answer, then it's probably just 5. But 5 over 1 will be most likely equally accepted. All right, now what does that mean in terms of the problem itself? So interpret the slope. We're going to do this kind of the same way we did explain the y-intercept, where you have to look at what this is really saying. What does it mean? Yep, m is 5. Or again, 5 over 1 is the preferred way to do it when you're then going to interpret it. So similar to what we did back here, where we said, yeah, so the value is 5. The way that I usually prefer to see it is 5 over 1, so that you can interpret it using language. So just like we interpreted this individual point, 0, 25, which meant after 0 days, the bamboo's height is 25 centimeters. Here, we want to interpret the slope. So what does this actually mean? +10 divided by +2, or 5, or 5 over 1. Take your pick, right? Whichever one you want to use, you can do that. Yeah, I hate the mnemonics. So you have to set up the definition of what the sine and what the cosine and what the tangent are in the first place. What do they actually mean? And then once you say, okay, this is the definition of this thing, and I'll draw you a diagram in a second here. Once we get past interpret the slope part. Okay, so when I say interpret, little player, this is going to be the same thing that we were doing with the point, where we said our point 0, 25 became, after 0 days, the bamboo height is 25 centimeters. So now we come back over here and say interpret the slope. What does positive 10 over positive 2, or what does 5, or what does 5 over 1 mean in terms of this whole problem here? Like, what is it doing with this line? What does it mean? Now, this is not a super easy question if you've never, like, been really engaged with it. So, you know, don't feel bad. And struggling with it is kind of the point. Because if you struggle with this stuff, then get through it. You can be like, now I get it. You remember the struggle. You remember how hard it used to be. And so, no, so if we look at, where is this thing going? There we go. If we look at the diagram, right? We already said from earlier, part D, right? Number 1, how tall is this thing after 5 days? Well, after 5 days, it's 50 centimeters. This was another point, 5, 50. And this was also another point, 2, 35. How tall was it after 35? Or no, how tall was it after 2 days? Well, it was 35 centimeters. These are points. The slope is talking about the trend. So, like, how is it moving from one point to another? So it started at 0, 25 here, and it got to 2, 35 here. What does that mean in terms of the variables that we're using? There is an increase of how much? You got it. So how much is that increase? Of 10 what? I'm going to be a massive pain about this, by the way. Just to warn you. So what are your units? What are you using? Plus 10 plus 1? Oops. So 10 height units for every one time unit. So from 0 to 25, we only increased 1 day to get to 35. After only 1 day? Yeah. So like look at the numbers we got up there, right? You're almost there. Yeah, I learned about it first at the National Council for Teachers of Mathematics, NCTM, in like 2011, 2012, something like that. I was like, oh yeah, this is so great. And then, like, I use it in my class all the time, but at the same time, like, it's a huge time suck, especially when you're like, especially when you're on a crunch, right? You've got to get through a certain amount of material over the semester. But, you know, 15 years, I've managed most of it. But is it 1 day? Two days, there you go. Right, this is why I said check this fraction here. So if you keep checking this fraction, that's where your that's where your numbers are going to come from. Also, watch your variables because you've switched your ordered pairs. So 2, 35, 0, 25, because it matters. That's also possibly where you were getting the inverted fraction from. Is that you did it correctly, but you used the numbers in the backwards order. So, I don't know, maybe. There you go. Auto fix. So when it's asked for you to interpret the slope, the first words that I would put down is for every. Because if you look at the rate of change in the height of the bamboo between 235 and 550, this is the same rate of change that's going on between 0.25 and 235, and also between 0.25 and 550. Right? It's taking here, going up 10 takes 2 days. Okay, from there, it takes 3 days to go up 15. Well, 15 divided by 3 is still 5 over 1. It's the same number here. And then if we started from 0 and went all the way to 5, that's 5 days to get 25 centimeters. So 25 over 5 is also 5 over 1. Yeah. Yep. And, you know, you can decide if you want to do that as every 2 days or just for every 1 day. All right, it's going to grow 5 centimeters. For every 1 day that passes, the bamboo grows 5 centimeters. And again, yep. Whatever fraction you want to use to do that, it's fine, because it's all the same ratio. The ratio is what's important. So even if it's not the most simplified ratio, like, I don't care. Maybe your teacher does. Maybe they want you to do the most simplified ratio, and that's the only way. Maybe. All right. So the formula for this, m is equal to, you already did it down at the other part here. Right? It's this stuff. 8 minus 3 over 4 minus 1. Right, this was 8 minus 3 over 4 minus 1. Which, again, where did this come from? Well, we wanted to know what was the difference in the y values divided by the difference in the x values. How do we do that? Well, we said this was going to be then, the difference in the y values is going to be this one here. And if you label them with what you normally label them, so like x1, y1, x2 to 2, ugh, y2. I really, really, really don't like the web-based version for this thing because it tries to take a weird sampling rate or something. I don't know. All right, so then that means that here, 8 was y2. 3 was y1, and we subtracted them. And on the bottom, 4 was x2 minus x1, which was 1. So our formula is just that. It's going to end up being y2 minus y1 over x2 minus x1. Keeping in mind, of course, that it is arbitrary which ones you label x1 and x1, y1, and x2, y2. You could have swapped all of them around, because if we swap them all around, I don't know if you've seen this before, but this will be equal to 3 minus 8 divided by 1 minus 4. Right, this is just going to end up with a negative 5 over a negative 3. Well, that's not a problem, right? We just say, okay, those are just going to be positive now. Divide both top and bottom by negative 1. Okay, so now, how do you create the formula or the equation for this whole situation? So start on that. Oh, man. Itchy nose. Start on that. And I'm just going to, real quick, where am I? Come on. I'll lose it again. I did. There we go. All right. So we start with our angle theta. We drop an altitude from our particular location, x comma y. Because, and again, this is sort of important. Let's actually not put that there. Right, the distance that this triangle has for its horizontal side is x. It's the distance that we have in the horizontal direction up to this particular point. And then again, for y, it's the same. It's this little triangle that's in here. All right, and our radius here doesn't actually matter how big the radius is. I'm perfectly fine with this. Okay. Now, we have to define some of this stuff. So if we go with it, we could just say, okay, the sine is going to be the ratio between the really hate the web app. Okay. Alright, so ratio between the opposite side length and the radius. So we kind of have to cheat a little bit and just say, like, this is what we're going to get. So sine of theta is just going to end up being our y value divided by our r value. And say, like, all right, well, unfortunately we have to come up with one definition. Then, I don't go to cosine next. I actually say, look, you all have heard about this thing. Right? What structure is this? Oh, well, that's a tangent to a circle, right? So, okay, if this is the tangent to, like, yeah, we need one definition. That's all we need, realistically. So here, we can start constructing this off of what we have. So here, the tangent line to the circle at this particular point is going to be this line. Now, we can define the tangent line or the tangent length of that particular angle to be pretty much anything we want, but we're going to say that the tangent length is the distance that goes between our connecting point here and the x-axis here. And actually, let's do it a slightly different way. Let's do it as just d for distance at the moment. Now, this makes a right triangle. it also shares angle theta. And it also shares a side nope, sorry. It shares a different side. That's why I'm yep. That doesn't work that way. Alright, so this means that we have now two angles, which are the same. And the side length, which is the same, is the hypotenuse on our XYR triangle. And the DR triangle, it's going to be one of the legs. So again, can't really do anything there. But this does mean that we can make this into a ratio because they are similar triangles. So our D value can be set up into a ratio, this being the short side of the triangle, opposite the angle, is going to be put into ratio with Y. Which is going to be equal to, and now we can put this in ratio, or say it's equal to, the ratio between, let's not do the hypotenuse, let's do the other length. So this is our R value, and this is our X value. Right, big to small, D to Y is going to be, D triangle has R over X. All right, now, if we want to scale this thing down so that it is on a unit circle, then what we have to do is take all of our measurements that are on the big triangle and scale them down by a factor of R. So how do we do that? Well, D over R means in extremes theorem, you can swap any two diagonals. D over R is equal to Y over X. And in fact, you don't even have to swap Y and R. You could, if you wanted to, just move Y to the other side, leave R where it is. But at any rate, D over R is going to get us a unit circle now. Yep, understood. Have fun, little player. Good luck. No problem. Yep, see you next time. Okay. So our unit circle here, D over R, is going to say that if R is equal to 1 now, that this tangent line is going to be like the idealized tangent line, the tangent line on a unit circle. So this is going to be our tangent of theta is now equal to Y over X. And where did that come from? Well, it's similar triangles and drawing a tangent line, which as long as you remember... I mean, it's not like, oh, it's swapping. So the means and extremes theorem is what people know of as cross multiplication, but I hate the term cross multiplication. This is the only time that I allow my students to actually use cross multiplication, because literally that's what it is. It's, you know, I can multiply the things that are diagonally opposite from each other without penalty. All right. Then all right, then I can also create another distance with that same triangle and say, hey, wait, if I go from here to here, ooh, there we go, then this distance I could label D2 or whatever I feel like. So this is going outside the circle here. This is going through the circle at 2 locations instead of just 1 like our tangent was. So we could label this as, again, anything we want. I guess just d prime. That's a terrible idea. I don't like that. E. So then if we look at similar triangles, again, we say that, oh, well, this is going to say that E, and this, for that triangle, is the hypotenuse. So the big hypotenuse is E, the little hypotenuse is R, is equal to, and now we want a big side and a little side that we know in this triangle. Let's not use D because we just found that. So let's use R, which is the leg that is adjacent to theta. So R over, and then the leg that's adjacent to theta is x, or has distance x. So E over R is equal to R over X. Again, we leave this as the idealized version of E, which is going to be on the unit circle. Let's scale it down. So this is R over X, which is the secant theta. It's going through the circle at multiple points, therefore it is a secant line. It's not the secant line, it's just a secant line. But it is a special secant line because it connects with the tangent that we just created. Alright, so again, instead of doing like E over R, well, let's solve for E and move R over to the other side. Let's not do that. We have this now scaled down to the idealized unit circle. So we can just leave it like that and then say, well, this is the definition of the secant function. It's one where it goes through the circle at multiple points. And the secant is specifically R over X, which we don't know what that is. We totally don't know what that is yet. You're going to like the next part. Alright, so these are the 3 main functions. And if you're like, wait, I thought sine, cosine, tangent were the 3 main functions. No, I've reframed everything. No, so a secant line will intersect a curve in two or more spots, but for a circle, it's going to be 2. And like locally, it's going to intersect in 2 or more spots. So when you just talk about generically a secant line, it's going to go through that curve at least twice. When you talk about the secant line for a circle, like of an angle, then we're saying, okay, based on that angle that we have, I'm going to build a specific secant that connects the origin out to the tangent function, or out to the tangent line that we just drew. Alright, there are multiple different ways to do it. This one I actually like better. I have another one that I can show you in just a minute, but it gets kind of funny. Okay, so draw the circle again. Drag this. No. Split. Can we split? Oh well. do it like that. There we go. Alright, so roughly the same angle. I'm never going to be able to duplicate it on the same graph. It's just not possible. We draw in the tangent line again. Oh, come on, really? Now you're not going to... What is that? No. I don't like that. Okay, there we go. There we go. So we draw in the tangent function again, all this stuff. Next one. Instead of going down, we go up. And we see where this is going to connect with our other axis. Now this is a tangent, right? This is also a tangent. However, this is the tangent not of theta. This line here is the tangent of alpha if we let alpha be this angle here. Now, what's the relationship between these two things? Well, they add up to 90 degrees, so that makes them complementary. So they're complements of one another. See it? The tangent to the complementary angle of theta is the cotangent of theta, is the tangent of this complementary angle alpha. So this right here, this is your cotangent of theta. So this distance that goes from this point here all the way down to this point here, that's your cotangent of theta. Which again, if you do this on the, you know, all these other ones that we were talking about before, you say, okay, this is just going to be f for now, and then f compared to, this is the tall opposite leg compared to, oops, wait. We gotta flip it around a little bit. Yes. Yep. And also, think about it. It didn't dawn on me until, like, somewhat recently. I was like, oh, really? I've been missing all that context for so many years. It's freaking ridiculous. Okay. So if we did this again, looking at it with just a regular sized triangles of any size, right? This works for any size. We say, okay, do f divided by, this is the long side, which, again, if this is alpha, this is theta. So this is adjacent to theta. What's adjacent to theta? Well, adjacent to theta is our x, going all the way back to the beginning. Or you could draw in these and say, oh, well, it's the opposite side to alpha, which we want the opposite side here. So f, the opposite side, compared to alpha is compared with x is equal to hypotenuses. Or, no, short legs. So the short leg of the big triangle is r, over the short leg of the small triangle is y. Which then, again, makes f over r equal to x over y. And again, f over r we label as cotangent. And you also know that x over y is the same as 1 over tangent of theta, which is y over x, right? The reciprocal. So this is one of the things. I can knock all these different relationships out in like one day. The students look at this and go, what the... Are you serious? Like, is that how this really works? They're like, yep, that's how it works. Oh, by the way, right? Go back to the other triangle that we have back here. What's the relationship between D, E, and R? R squared is equal to... Nope. R squared plus. Damn. R squared plus D squared is equal to E squared. Well, if we divide by R squared all the way through, we get 1 plus D over R parentheses squared equals E over R squared. Which then, again, D over R was tangent of theta, E over R was secant of theta. So 1 plus tangent squared theta is equal to secant squared theta. Right? Pythagorean theorem. Now, I do question my wisdom in going for cotangent first instead of cosine, but whatever, it's fine. Alright, so then if we look at the, again, here, we can go with whatever we feel like. Let's go with complementary sine. Right, again, cosine. The cosine of theta is going to be equal to the sine of alpha. So what's the sine of alpha? Well, that's going to be x over r. Because we want everything in terms of theta, right? We got to think of it in terms of, oh, well, this is the sine of the complementary angle to theta. So it's x over r. Oh, by the way, we had a thing about that up here. The secant was r over x. So this also means that cosine of theta is going to be 1 over secant of theta. All right, and then we do the other thing here. We say, okay, what's the last one we want? Well, that's going to be this length here that goes out to the cotangent. What is that? Well, that's the secant, but it's the secant of the other angle, the secant of alpha. So that is the cosecant of theta. right? And we could do the G thing if we wanted to here and just say, okay, well, this is G. So figure out the relationships again. So G over, this is the hypotenuse of the big one, over the hypotenuse of the small one is R, is equal to sides. Again, small side is going to make this easier. So opposite theta is R over opposite of theta here is Y. So this is cosecant theta is equal to R over Y, which is 1 over sine of theta. Right, complementary secant, complementary tangent, complementary sine. So this is one of the reasons why I do this specifically in this-ish order, is talk about the sine, secant, and tangent first, and then talk about all of the co-functions second. So that also means that if you wanted to do this, you could say here, well, the cosine of theta is equal to the sine of alpha. Okay, well, that also means then, since theta plus alpha is equal to 90 degrees, or pi over 2 radians, however you want to do, this can be, well, alpha is then equal to 90 degrees minus theta. So then here, cosine of theta is going to be equal to the sine of 90 degrees minus theta. Now you've done your cofunction identities, because all of them end up doing the same thing. And then go through and say, well, what about the sine of alpha then, or sine of theta? Wow. What about the sine of theta? Well, the sine of theta is going to be equal to the cosine of 90 degrees minus theta and all that. So sine, secant, tangent also have their cofunction identities. Just ends up being a replacement, one for the other. That's all algebraic, pretty much, right there. So yeah, this is my favorite picture to work with. This also then gives you the same deal. Secant squared is equal to tangent squared plus 1 squared, or cosecant squared is equal to cotangent squared plus 1, or the inside here ends up being sine squared plus cosine squared equals 1. So I use all of them, show them all off. So the other diagram that I had been using up until this point The other diagram I had been using was this. Which again, still gets us the whole sine cosine thing. That's not an issue. But when it comes to the tangent, so what we have is a vertical tangent here. And again, assuming that r is equal to 1 for the unit circle. This distance here is going to be the tangent of theta. Yeah, no problem. And then also the secant is going to be this distance here, which shows you that it goes from the origin out to where the tangent meets it. This is okay, but I have problems with it because if you rely on it too heavily, what'll happen is as you go past pi over 2, you're now over here. So your terminal side's over here, your tangent is over here. So how do those connect? You can go about it a couple of different ways. One, you start on the negative side and you say, well, it's connected to the negative tangent. Or you go and you say, I can extend my terminal side into the opposite quadrant, because that's how tangents work, right? It's a line. You just continue it into the next quadrant. Sure, I guess. And that means that it'll be connected to the negative side of the tangent line. So, like, this is of some use, but it gets to be a little bit weird when you start dealing with stuff that's beyond the first quadrant. So I don't find it extremely useful anymore, especially since the other thing you have to do is start looking at, well, what about a cotangent? Nope, not there. I can't hardly see that. That's awful. It's just enough different that that's irritating me. So the cotangent goes out to the terminal side. Which means the cosecant goes out to there. So, like I said, this gets really kind of messy, and I don't like it as much. This one over here on the right is much cleaner. It only allows the one tangent cotangent line to be drawn, and it fits rather nicely with it. Okay. Well, thanks for stopping in, everybody. Awesome job tonight. If you want more explanations of weird stuff like this, especially trigonometry, because this is like my bread and butter course, like I've said, I have taught this course the most at my entire institution, and I've only been working there for like 11 years, so or doing this level of course for 11 years. So it's yeah, it gets to be fun. No, don't want to do that. Damn. All right, so we're gonna figure out who to raid tonight. Alright, I think Boss Lady is probably our best bet. She's doing some xenobiology and Elite Dangerous. Devastator is doing Dead by Daylight, but he's not going to be on that long, I don't think. Yeah, no problem, Killer King. Anytime. And let's see, Hanzo Gonzo is doing Guild Wars.